This is Physics 102B at Porterville College, Chapter 25 homework, starting with problem number 29. The problem just asks to write the isotope symbol with the atomic mass at the top and the symbol. And so 24 protons and 25 neutrons would give you, for the first one, an atomic mass of 49. And you can look up in the periodic table and see that the atom with 24 protons is, I have the symbol Cr there, that stands for chromium. For part B, the 43 protons, you look that up in the periodic table and you see that's technetium, which is Tc, and you add up the protons and neutrons, that gives you atomic mass of 94. And finally, lead 190 would be the third one. Number 31, find the number of protons and neutrons in bromium 80. So you have to look up the symbol Br, or bromium, in the periodic table. And you find that that's element number 35, which means it has 35 protons. So you take the mass of 80, subtract 35, and that gives you 45 neutrons. And similarly, krypton 80, you look it up in the periodic table, you see krypton has 36 protons. So 80 minus 36 gives 44 neutrons. Question number 33 asks for the nuclear radii for those four isotopes. The main formula you want is that it's the cube root of the atomic mass times 1.2 femtometers. And so you just plug in the atomic mass of each of those, starting with part A, lithium 7. That means you're taking the cube root of 7. And you get those answers written on the screen. Next we have number 35. What's the nuclide whose nuclear diameter is closest to twice that of aluminum 27? If the diameter is twice, then the radius is also twice. And rather than solving for the diameter directly, I just did some algebra here. So we start with the first line saying the radius that we're looking for is twice the radius of an aluminum nucleus. And then I make the substitution. For each of those radii on the left-hand side, the radius of the mystery nucleus is 1.2 femtometers times its mass to the third power. And on this side you have your 2 times the radius of the aluminum, 1.2 femtometers times the cube root of 27. The 1.2 femtometers divides out of both sides of the equation. You're left with the cube root of the atomic mass equals 2 times the cube root of 27, which is 3. So cube root of the atomic mass is 6. Cube both sides of the equation, so we get atomic mass is 216. So there's no one particular one that will give that, but any nucleus whose mass is 216. And there are several isotopes that do that. Number 47. Write the full reaction for the beta-negative decay of copper 67. So I've written, I want you to notice I've done this the way I've done it in class. Now you should know officially these are not the symbols that you put next to beta negative. I've just put them there for instructional purposes, that they really help having the 0, which signifies a relative mass of 0, and -1, meaning the charge of -1. And that helps the arithmetic. It helps this process a lot. But you should know that officially the 0 and -1 don't go there. So we say 67 equals 0 plus what? 67. And down below for the charge, 29 equals negative 1 plus what? 30. And that tells us that the element we're looking for is 6730. We look up element number 30 in the periodic table and we see that we're looking for zinc 67. And a similar process was used to find the other two answers. So for part B, element 37 is rubidium, and for part C, element 47 is silver. Number 48 and 49 give you more practice. Let's zoom in a bit more here. Okay. So it's fill in the blank, and you use similar procedure. And I do recommend that for that beta negative that you write for yourself for this beta negative that it has a charge of -1 and a mass of 0, and that'll, like I did in the previous problem, and that'll make the math go more smoothly. But so there are the fill in the blank answers. For number 48, it's beta negative. For the next one, it's gallium 66. And then francium 209. And then bismuth 210. And that's an excited state of bismuth 210. Remember that for gamma decay, there is no transmutation of the nucleus. It stays as the same one. Number 49, more fill in the blank. So you can see the answers there. I want to point out something that also applied to the first one on number 48. When you're doing this part B, the math, so it says the mass goes from 178 equals 178 plus what? And you can write in for yourself. So when you're first doing this problem, you don't know that the answer is going to be beta positive. So you do the math and you just fill in a 0. And then 72 equals 71 plus what? Positive 1. And that 0 and positive 1 tell you then that you're dealing with a beta positive. Next is number 53. Alright, for 53, we're dealing with radon-222. There's a limit for safe exposure, 4 picocuries per liter. What is this activity in becquerels? So the conversion is right here. 1 curie is 3.7 times 10 to the 10th becquerels. By the way, remember a becquerel is a decay per second. So we start with our 4 picocuries. That's 4 times 10 to the negative 12 curies. We do that conversion and we get 0.148 becquerels. And it's actually becquerels per liter. Part B, recognizing that a becquerel is a decay per second, we call that 0.148 decays per second multiplied by 86,400 seconds in a day. And here we're left with 12,787 decays per day. And actually that would be decays per day per liter. '57 gives practice with half-lives. A very short-lived isotope, oxygen-15, has a half-life of just 2 minutes. We start out with 2.60 milligrams. So in 6 minutes, how much time has gone by? I've written out for you two different ways to solve this. So one way, you could do this without doing any intense math, because this problem happens to work out to even numbers of half-lives. Most often, practically, that won't be the case. But even if this doesn't work out exact, you can still get an estimate. 6 minutes, a half-life is 2 minutes, so it's 3 half-lives. So you cut the initial amount in half 3 times. So 2.6 gets cut in half to 1.3, gets cut in half to 0.65, gets cut in half again to 0.325 milligrams. Now, right here, I show you the proper way to solve it. As I said a minute ago, most often in practical situations, it's not an even number of half-lives, so you can't just cut in half an integral number of times. So here's the proper formula. The mass at any given time is the initial mass times 1/2 to the x power, where x is the number of half-lives that go by. So 2.6 times 1/2 to the, and the exponent is 6 minutes divided by 2 minutes, or 3 half-lives. And you also get the same result, 0.325 milligrams. Now the next part involves 10 minutes after the delivery, or 4 minutes after the 6 minutes have gone by. So I have on the left and right hand side of the page two separate ways of solving it. On the left hand side is from the initial from the initial time when it was 2.6 milligrams. Okay, 2.6 milligrams when it was initially produced, times 1/2 to the, and it's 5 half-lives, 10 minutes divided by 2 minutes. Or you could do it on the right-hand side. It's been 4 minutes since the delivery. So 0.325 milligrams, which is how much was delivered, times 1/2 to the, and the exponent is 4 minutes over 2 minutes. 2 half-lives have gone by. Either way, you get the answer, 0.08125 milligrams. Number 63. Now we're dealing with tritium, half-life of 12.3 years. If we have 2,500 kilograms stockpiled, how much would remain after 100 years? Okay, pretty straightforward. Here's the problem. And I've used capital N's, although technically these should be lowercase m's for masses. But it's the same formula either way, whether we use mass or number of nuclei. It's going to be 2,500 kilograms times 1/2 to the power of how many half-lives go by. So the number of half-lives is 100 years divided by 12.3 years. So it's going to be 1/2 to a little more than the 8th power. That, you can see in the next line, reduces it to 0.003569, or 0.3% of the original amount. So it comes out to 8.9 kilograms. Number 64. Americium 241 with a half-life of 433 years. And the question asks, if you keep a smoke detector 5 years, by what factor is the activity reduced? Okay, we haven't yet covered in this homework activity, but I want to show you the bottom line is this equation right here, that R is equal to r naught times 1/2 to the x power. The same what we did for n or for m, it works for activity also. And just to show that algebraically, up here, activity, you learned in class, is lambda times n. So if I take the half-life equation with n, and I multiply that entire equation through by lambda, and then I can replace lambda n and lambda n naught with r and r naught. So activity, r, works in this equation as well, in this format. So we can say r equals r naught times 1/2 to the, and here comes how many half-lives have gone by, 5 divided by 433. Not much has gone by. So it turns out r naught, or r is equal to 99.2% of r naught. It hasn't been reduced by much. So if it's 99.2% of the original, that means it's been reduced by 100 minus that, or 0.8%. Let's take a look at part B. Part B says, how many years pass before the activity falls to 99% of its initial value? Well, after 5 years, it's already fallen to 99.2%. So you can estimate it's not going to be too much after 5 years that it's going to go that little bit more down to 99% even. The way we can set this up, using the same r equation, but solving it for t, we divide both sides of the equation by r naught, and we have r over r naught, which we're then going to replace by 0.99, equals 1/2 to the t over 433. Now we're solving for t. We set it up as a logarithmic equation. So remember, converting from a exponential equation to logarithmic, we take the base, and that'll 1/2, that'll be the base of the logarithm, of 0.99 is going to equal the exponent. So we have log base 1/2 of 0.99 equals t over 433. We multiply both sides by 433. Remember one of your rules of logarithms, if you need the log with some base that is not 10 or e, as in this case, just do log of the number divided by log of the base. So t equals 433 times the ratio of the log of 0.99 divided by log 0.5. And that gives 6.28 years. About what we expected, a little more than 5 years. Number 71. Complete the following fission reactions. Okay, so you got practice at this back in homework problems 47, 48, and 49. It's the same concept where you do the math to fill in the blank and just remember that the number up top, which is mass, has to be conserved, and the number down below, which is charge, has to be conserved. So with this problem, with part A, remember there are 3 neutrons, so that'll count as 3. So you ask yourself, 1 plus 235, which is 236, equals 144 plus what? Plus 3. And that gives a top number of 89. And the bottom number, 0 plus 92, equals 56 plus what? Plus 3 times 0, which is 0. And so you should get krypton 89 with atomic number of 36. And you can see similarly for part B, we have element number 57, lanthanum 143. And for part C, we get an atomic mass of 40, which is zirconium 96. I'm sorry, atomic number of 40, which is zirconium. Has a mass of 96. Okay, last one. number 93. Safe for human consumption. Okay, so iodine 131 has a half-life of 8.06 days. That's something you can look up in the back of the book. I also talked about it in class. There was a claim that it would be safe, the milk would be safe within 5 days. Initial activity was 2,900 becquerels per liter. Sweden's safe limit, what they declare to be safe, is 2,000 becquerels per liter. Is the 5-day figure accurate? The easiest way to do this is to see what would happen to 2,900 becquerels per liter activity of iodine 131 after 5 days. So I set up this equation. The activity is the initial activity, 2,900 times 1/2 to the 5 over 8.06, and I get that it's 1,886 becquerels per liter. And since it's below the limit, according to the government of Sweden, then yes, it's safe. And that concludes the Chapter 5 homework.